Okay, so we begin this course by studying the physics of the MOSFET. We'll take a very quick look at how the MOSFET works and some basic effects that have an impact on the circuit behavior of the transistor. So MOSFET is, as you know, of course, is metal oxide semiconductor field effect transistor. Of course, the latest MOSFETs don't necessarily have a gate that is made of metal. It could be made of polysilicon. The oxide is often a mixture of oxide, nitride, etc., etc. But the name has stuck, MOSFET. And this is a kind of schematic of a MOSFET. So this is a bulk MOSFET. So there is a P-type substrate here, on top of which there is a very thin gate oxide, on top of which there is a conducting metal or a polysilicon, which is called the gate. On either side of the gate are N plus regions, plus the plus indicating very heavily doped, and they are contacted. So on top of the N plus region there is a metal contact here, and there is a metal contact here. So these are called source and drain. Usually source and drain are interchangeable from the structure. In the structure of a MOSFET, one can use either one as a source and the other one as a drain. Which is source, which is drain is determined by the voltages that are applied to these terminals. And there is a contact to the p-type body or the substrate. uh, Usually, of course, this is schematic. There is never a connection at the bottom of an silicon wafer. All contacts are at the top. But this is just a schematic to show that there is actually a contact. So contact is always made with a metal uh, on top of the semiconductor. For our purposes, we'll use this simplified schematic. We will not keep showing the metal. It's assumed that there is a metal here. And for this lecture, we'll assume that the source is grounded, the body or the substrate is grounded, and we are going to vary the gate and the drain voltages. Okay, so let us begin by applying a zero gate voltage and a very small drain voltage, and ask ourselves a couple of questions. So incidentally, so I have shown here explicitly that a PN junction, as you are familiar, has a depletion region around it. So the P side has negative fixed charges and the N side has positive fixed charges. So both these, the source body junction and the drain body junction, have PN junction, depletion regions without any voltages applied. Okay, so we apply a small drain voltage and then we ask our first question, will current flow anywhere? Will I have a voltage applied, will current flow anywhere? Now there are lots of terminals, so let's look at each pair. So the source and body junction has zero voltage across it, so there is no question of current flowing. The gate is also zero. In any case, I think you know that because there is an insulator between the gate and the body, current will not flow from the gate to the body. Well, I should say DC current will not flow from the gate to the body. The drain has a voltage, and so this NP junction, the drain body junction, is reverse biased because there is a positive voltage we applied at the N side. So the question is, will current flow in this drain body junction? And I assume you will say that because this junction is reverse biased, current will not flow. So the question is, why? Why do currents not flow in a reverse biased PN junction? The answer is of course correct, that they don't flow. But let us ask ourselves why currents don't flow in a reverse biased PN junction. Okay, now what I'd like you to do is, and I'll do this often in these lectures, I'll ask you to pause the video, and well, after you pause it, you take a piece of paper and you write your answer to this question. why do currents not flow in a reverse bias PN junction? And the purpose of doing this pausing is that you have to think as you progress through these lectures, because it is only when you think that you will be engaged and you will understand the depth of the concepts that we discuss here. Okay, so pause, write, and then continue. I'll of course continue this video because I don't want to keep the video blank for a few minutes and then continue. Okay, okay, so let's go ahead. Okay, so let's look at a just a simple PN junction. So I have a P and an N, and the P side is grounded, and we apply a positive voltage to the N side. So this is reverse biased, and there is some depletion region. And because this voltage is positive, current must flow from this positive to ground, which means that current must flow from the N side to the P side. Now, of course, current means positively charged particles. So, positive charged particles must flow from the N side to the P side. In a PN junction, positive particles are holes. So, they must flow like that. And electrons, they will be attracted to the plus. So, electrons must flow from the P side to the N side. So, this is what must happen for current to flow. Alright. Now, the reason current does not flow in a reverse bias PN junction is because if we look at this, we want electrons to flow from the P side to the N side because of the polarity of the voltage. There are very few electrons on the P side. Similarly, there are very few holes on the N side. Therefore, there is no possibility of maintaining continuity of current from the, okay, let me rephrase. The fact that there are very few electrons on the P side means that very few electrons will go from the P to the N side, very few holes will go from the N side to P side, and therefore the total current will be very small. This is the reason. There are many, my guess is that you wrote, if you did pause and write, you would have written some other answer. Correct answer is this. There are very few, and what you probably know that electrons on the P side are called minority carriers. Holes on the N side are called minority carriers. And a reverse bias junction carries a very small current because there are very few minority carriers. Okay. That's why, and we say this current is so small, basically we say it's for all practical purposes, it is zero. Okay, so we go back to the MOSFET. So we say, okay, for these voltage conditions, no currents flow anywhere. There is that small reverse biased, what is called as a leakage current that flows, we'll ignore it. We'll say that is close enough to zero that we can ignore it. Okay, now we say let us increase slowly the gate voltage. So we say what happens now if a small gate voltage is applied. So you have a positive, okay, a positive gate voltage is applied. So now this basically is a capacitor, metal oxide semiconductor. Metal is conducting, semiconductor is reasonably conducting because it is doped. So a positive voltage to the gate will cause positive charges to accumulate at the metal surface closest to the semiconductor, and the positive voltage will push away or repel away the holes from the semiconductor. And in a semiconductor, in a p-type semiconductor, there are freely moving holes and there are fixed acceptor ions which are negatively charged. So in a neutral p-type material, there are as many holes as there are negative acceptor ions, and so the material is neutral. When we push the holes away from the surface, they leave behind negative acceptor ions, and so there is a negative charge near the surface. This is called a space charge region or a depletion region. It is called a depletion region because it is depleted of holes. There are no holes left. So this is what happens. There are fixed acceptor ions, they cannot move. There are positive charges in the metal, or one should not say, yeah, okay, positive charges, not discuss this further. Okay, will current flow? There is a gate voltage, there is a drain voltage. Will current flow? Current will still not flow, all right, because there is no place for it to, well, okay, current will not flow. Again, I am emphasizing here, no DC currents flow in the gate. The gate has a positive voltage, but because this is a capacitor, DC currents don't flow from the gate to the substrate. AC currents can flow. Any capacitor, if the voltage on the gate is changing with time, current will flow like in any capacitor. But DC currents do not flow. Okay, let's increase the gate voltage. So we keep increasing the gate voltage more and more and more. So more and more positive charges accumulate on the gate metal near at the surface. By the way, this is shown like this, but of course you know that charges in a metal can exist only at the surface of the metal. This is just a pictorial representation. So more positive charges here, there have to be more negative charges here. So more and more holes get pushed away from the surface. Slowly electrons start getting gathering at the semiconductor surface. All right. And as the gate voltage is increased, there are more and more electrons that gather and form what is called as an inversion layer at the surface of the semiconductor. I assume you know this. Inversion because this charge is the opposite of the free charge in the body. So this is P, this is hole, so these are positive and this is negative, so you say inversion layer. An inversion layer is also called a channel. A channel is basically a path of conducting carriers that connects the source to the drain. So now there is a conducting path from the source to the drain, all of electrons. There are electrons in the N region here, electrons here, and electrons here, and so current can flow from the source to drain now. So for a large enough positive voltage, current can flow from the source to the drain when, of course, a drain voltage is present. Okay, let us talk a little about the threshold voltage. Again, I'm assuming you know the term threshold voltage. The threshold voltage is defined as the gate voltage at which the electron density in the inversion layer becomes equal to the hole density in the substrate. Alright, that is the threshold voltage. So if we go back here, as we increase the gate voltage, the electron density in the inversion layer is increasing. At some gate voltage, this electron density is what? Number of carriers per unit volume. When that becomes equal to the number of holes here in the neutral region, at that voltage, we say that gate voltage is defined as the threshold voltage. Alright. There are actually other definitions of VT also, but we will use this definition for our purposes, for our analysis and simple models that we will use to solve circuits. In a the simplest MOSFET model, one assumes, and we will do this throughout this semester in fact, that for gate voltages less than the threshold voltage, no current flows in the MOSFET. This is of course only an approximation. So again, if you think about it, as the gate voltage is increasing, slowly electrons are gathering at the interface, and that process of gathering is slow. A little higher gate voltage, a little more number of electrons, higher. At some point when that density becomes equal to the hole density in the substrate, we say, this is threshold voltage. So even for a VG less than threshold voltage, there are of course electrons present. Therefore, current actually does flow in a MOSFET for gate voltage is less than the threshold voltage. But for our purposes, just to simplify the analysis of circuits, we'll assume that the current is zero. The assumption is justified only because the current is very small. So we say, okay, it is so small that we'll assume it to be zero. The current that flows for Vg less than Vt, because the electron density is small and the current is small, that current is called as a sub-threshold current, and the region, the electron, this region is called as weak inversion. So the inversion layer is weak. So we say for Vg less than Vt, there is weak inversion in the channel. For Vg greater than Vt, there is strong inversion in the channel. All right. Okay, so let us say that we have applied some gate voltage greater than Vt, and now we want to apply a larger and larger drain voltage and see what happens as a larger and larger drain voltage is applied. Now, as we increase the drain voltage, we must recognize this very important property or characteristic of this structure. So we have a gate voltage which is causing a vertical electric field in the in this region, in the MOSFET. When you have a drain voltage, we have a electric field that is lateral in the channel. Of course, the drain voltage causes electric fields everywhere, but we are worried about what is happening to the channel. So the channel is here, and as the drain voltage is increased, it is causing a change in the electrostatic potential along the channel, right? If the drain voltage was zero, this is also zero, then from source to drain there is no lateral electric field. But as the drain voltage is increased, there is a lateral electric field from the source to the drain. Let us say Vd is 0.5 volts. So if this is 0.5 volts and this is 0 volts, what this means is that the electrostatic potential in the channel due to the drain will vary from 0 here to 0.5 here. Alright, so it is changing from 0 to 0.5. And that electrostatic potential variation from the source to the drain is often called as Vy, where y is the axis along the channel, this is y, and x typically is defined as going deeper into this body from the surface. I have not shown x here because it is not of relevance to us. But for our purposes, we will define the source edge of the channel as y equal to 0, the drain edge of the channel as y equal to L, and we say the electrostatic potential at the source edge is 0 at the surface, and at the drain edge it is Vd. This is only due to the drain voltage. There is another electrostatic potential due to the gate voltage which I am ignoring here. I am simplifying this drastically. Alright, but so with this we have a Vy that varies from 0 to Vd, from source to drain. Okay, now we say, let me see. Yeah, okay, let us think about this. So when we have a drain voltage that is greater than 0, what we will say is that the gate to channel voltage at any point in the channel, and let's say specifically here. So let's say the gate is 0.9 volts, the drain is 0.5 volts, then the potential difference between this point, this of course is entirely 0.9 volts because the metal is an equipotential. So we have a 0.9 volt here, we have a 0.5 volt here, which means that, now let me say this is 0.3 volts. So 0.9, 0.3. So we have a 0.9 minus 0.3. This potential difference is 0.6 volts at the drain end. At the source end, this is 0.9 minus 0. So this potential difference is 0.9 volts. So 0.9 here, 0.6 here. So clearly the potential difference between the gate and anywhere in the channel varies when there is a drain voltage applied. Now, if the potential varies, what that means is that the electron density at any point in the channel is going to be varying also, because the potential, if this is 0.9, that's a larger vertical electric field, and therefore more electrons will be present here. This difference is 0.6, so fewer electrons will be present here. In fact, to quantify, one says that for an inversion layer to exist, the gate minus this surface potential Vy, Vg minus Vy must be greater than Vt. Alright, only if it is greater than Vt will a channel exist. Alright, this has two implications also. The third one we'll come to in a minute. One implication is that the fact that the inversion layer density is changing, right? The inversion layer density keeps changing as the drain voltage is increased, means that the total amount of conductivity of the channel is reducing as the drain voltage is increased. And if the conductivity changes with a voltage applied, then the current will not vary linearly with the drain voltage. Alright, if the conductivity is constant, this inversion layer behaves like a resistor, and as the drain voltage is increased, the current will increase linearly with the drain voltage. But here the conductivity is decreasing, so the current will not increase linearly, but it will increase sublinearly with the drain voltage. That is one observation. The other is just an observation that although here I have shown this inversion layer thickness, this thickness it looks actually thick, but it's actually, the inversion layer is extremely thin. It is typically of the order of 10 angstroms. So you can't really, of course, you can't see 10 angstroms. So this is again as a representation. Similarly, the positive charge in the metal is also of the extent of 10 angstroms or so. Alright. Okay, so let us take a numerical case that Vg is 0.9 volts, and let us say the threshold voltage of a particular MOSFET is 0.4 volts. So when Vd becomes 0.5 volts, then Vg minus Vd, Vg minus Vd becomes how much? 0.4 volts. So this becomes equal to 0.4 volts, which is equal to the threshold voltage. And the threshold, we said that for just at the threshold voltage, for our approximate model, we'll say channel does not exist. All right, in our simple model, we'll say for Vg less than Vt there is no channel, Vg greater than Vt there is a channel. Okay, so at these voltages, we say in our approximate analysis that a channel stops existing at the drain end of the MOSFET, and that is called as pinch off, right? So here is a pictorial representation. So if we have some gate voltage, and if the drain voltage is greater than Vg minus Vt, if the drain voltage is greater than Vg minus Vt, then there will be a region here where no channel exists, because the gate to drain voltage is less than the threshold voltage. And because if it is lesser, then we say in approximate model that channel has stopped existing, and we say there is a region here that is pinched off. The term that is used is a pinch off region. Alright, so we were increasing the drain voltage slowly, keeping the gate voltage fixed. The current was increasing. Current was not increasing linearly, it was increasing sublinearly. Then at a certain drain voltage, suddenly the channel stops existing. What happens to the current? Will current flow? There is no There is no channel here. There are no electrons here. It's all fixed charges. So what do you think? Again, pause and think about this. Will current flow? And if it will flow, how will it flow? How can current flow if there is a pinched off region? Alright, pause, think, continue. Okay, I'll continue. Okay, let's go back to our reverse bias PN junction. So what we had said here was that if there is a positive voltage applied here, the fact that there are no electrons in the P side means that no current will flow in the reverse bias, or very small current will flow in the reverse bias PN junction. Now let us say that we shine light on the P side of the PN junction of an appropriate frequency. Now what does light do to a semiconductor? If the frequency is appropriate or high enough, then what light will do is, let's say there is a silicon atom, that light, the photon will hit an electron sitting or bound to the silicon atom, and it will provide it enough energy so that it will become free to move about, and it will leave behind a hole where this electron was sitting on this atom. In other words, light of an appropriate frequency will generate electron hole pairs in the semiconductor, that are free to move about. Electrons are already there, but now they are becoming free because they have acquired energy from the light. Alright, so if there is enough light shining, this region is getting a lot of electron hole pairs being created. Now what does that do? Suddenly, because there is light, there are lots of electrons here. Now if there are lots of electrons, they are available to carry current to the N plus side, to the positive voltage. So they'll all get attracted to the N plus side, and now a current will flow. Right? So even though the junction is reverse biased, the fact that we have created a large number of electrons, a large number of minority carriers on the P side, current will flow in this PN junction. This, of course, as you know, is the principle of a photodiode. This is how a photodiode works. When light shines on it, photodiode carries current. If there is no light, no current flow. In fact, this is also the principle of a solar cell, except that the solar cell is not operated with a reverse bias PN junction. It is operated with a forward bias PN junction. Okay, that's one thing. Another very important aspect is, so again let's think about, so there are lots of electrons here created due to light, and they are creating a current that flows through the depletion region. Alright, this is of course a depletion region, and a depletion region is called a depletion region because it is depleted of mobile carriers. To be depleted is that they are not available. There is no mobile carriers there. That's why it's called a depletion region. But when current flows, there are actually sufficient electrons passing through the depletion region to maintain the continuity of current. Alright, it's very important. Although one says that this is a depletion region, if I have lots of electrons here because of light, they are all getting swept across this very large electric field. So they'll move very fast across the depletion region because there is a large electric field. And so for maintaining any current, the fact that the velocity of electrons in the depletion region is very high because of the large electric field, the number of electrons required to sustain any current is small. But it is there. There are actually a small number of very fast moving electrons in the depletion region that sustain the continuity of current. Alright, let's look at another example. So this is our PN junction. The N was plus V, the P was grounded. Now let us say we added another N++ region, very heavily doped region to the other side of this P plus, and we applied a positive voltage to that N plus plus region. What happens here? This N plus plus P plus junction is forward biased. Oh, is it forward biased? I'm sorry, this is mistake. Sorry, this is negative. So we put a negative voltage source to forward bias the N plus plus P plus junction. So this is positive compared to this N plus plus. And so now this junction is forward biased. So holes will go from the P side to the N side. Electrons will go from the N side to the P side. And because there are lots of electrons, they'll go in large numbers. Holes will go in large numbers from the P side to the N side, and a large current will flow. This is a forward biased diode or a PN junction. So you know a large current flows. Now, but because of these electrons being injected into the P plus region, what we are doing is we are causing or creating a large number of electrons in this P plus region, because we are providing these electrons from the N plus plus side. So now again we have a large number of electrons in the P plus region, and because we have a large number of electrons here, this junction, although it is reverse biased, will carry a large current because we've made available minority carriers on the P side. So once again, a large current does flow across this reverse bias PN junction. Alright, this of course is a bipolar transistor. This is how a bipolar transistor works. Well, I mean, there's more to it, but this is one aspect of the working of a bipolar transistor. How a bipolar transistor has a large current gain is a separate discussion. If you want, you ask me and we'll discuss it at another time. Again, the point being that electrons are swept across this reverse bias PN junction, and so there will be a small number of electrons in this depletion region that will sustain the current. Alright, so now we go back to, okay, what do I have to say here? The pinched off region in the MOSFET is similar to a reverse bias PN junction. Alright, but it is a very complicated two-dimensional PN junction. Both these examples, this and this, were one-dimensional PN junctions because the electric field is only in this one direction. A MOSFET has a vertical field, a lateral field. It is very complicated, but ultimately it is a reverse bias PN junction. Alright, now in this reverse bias PN junction, we are let's go. Okay, we'll come back to this. So what we are doing here is, so this is our depletion region. There is a depletion region on the N plus side also, which I have not shown. There are positive charges here, which I'm assuming that they are there. So this is the NP depletion region, but there are no carriers here. But to the left of this depletion region, this N plus, this depletion region, to the left of it, we have electrons available due to the inversion layer of the channel. And we have an electric field that is trying to pull electrons to the drain side. So although there are no carriers here, the fact that there are carriers here is similar to the electrons on the P side of the reverse bias PN junction. Alright, as I said, this is complicated two-dimensional, but this is a P region, so PN junction. There are electrons available on the P side of the PN junction, and because there are electrons available, current does flow across this reverse bias PN junction. And so these electrons will be swept across at high velocity across this pinched off region and contribute to current. Alright, and so therefore there are actually a few a small number of electrons in this region that sustain the current. The reason one says that they are not inversion layer electrons is because these electrons, if you actually do a two-dimensional simulation, one finds that when they are swept across, the electrons will be all over the place. They will not be just at the surface, they will be flowing in the body also. The flow will be scattered or spread across a depth of the depletion region here. Alright, so the answer of course is that current does flow even after the channel is pinched off because electrons are available here. Okay, the other thing I was saying here was that once pinch off occurs, the drain current does not increase when the drain source voltage is increased. So once this has occurred, if I keep increasing the drain voltage, the current does not increase, it remains constant. One says that the drain current is saturated, it has become a constant. So why does it not increase? Why does current not increase once a pinch off occurs? Very simply, one says that, well, this is a high resistance region, and when the drain voltage is increased, the entire additional drain voltage falls across this pinched off region. So let us say we took the example of 0.9 volts here and a VT of 0.4 volts. So VD sat, which is VG minus VT, is 0.5 volts. So let's say VD is 1 volt. So what happens is this point, the point at which the channel ends, will be VD sat 0.5 volts, 0.5 volts, yes. Because the channel exists up to the point where Vg minus Vt is equal to the channel potential. So Vg minus Vt is 0.5. So the channel, wherever the channel potential is 0.5, to the left of it, inversion layer will exist. If Vd is 1 volt, the entire additional 0.5 volts will fall across the pinched off region. So if we make Vd from 1 to 1.5, the pinched off region will have 0.5 to 1.5, so 1 volt across it. This voltage will remain 0 and 0.5. Alright, so the any additional drain voltage falls across the depletion region. That is one. The other is the magnitude of the current in such a structure with such voltages is determined by the inversion layer. And the inversion layer has 0 to 0.5 volts. And therefore, the current being determined by this inversion layer remains constant. And then the additional voltage, drain voltage, can keep on increasing, but the current magnitude does not change. Okay, call it 0th order. First order, the current does increase a little because this depletion layer width increases a little as the drain voltage increases. So let's say if Vd goes from 1 to 1.5, this point, the point at which the channel is ending, moves a little to the left. It doesn't move much, but it moves a little to the left, and so the inversion layer length reduces a little. And of course current goes inversely as the length, like any resistor. So the length is slightly smaller, the current is slightly larger, but that change in current is small. Alright, and that is called as channel length modulation. When the drain voltage increases, the pinch off point moves to the left, and therefore the effective channel length reduces. That effect is called as channel length modulation. So channel length modulation causes the current to increase slightly as the drain voltage increases in saturation. Alright. Okay, so this is the end of this lecture. Next lecture we'll talk about the threshold voltage.